Hi, my name is Miloš and welcome to Element 14 Presents. Today I'll be talking about measuring cardiography signals. I'll show you how blood pressure monitors work, we'll do some ECG, we'll also measure some other heart signals as you will see along the video, and I'll show you how I made my own device. Let's dive right into it. Let's begin by talking about blood pressure. So there are invasive and non-invasive methods of measuring blood pressure, and of course we're going to be doing the non-invasive ones in this video. So the most two common ones that you could have seen are this one, which is the manual blood pressure measurement, and this one, which I would call the digital or automatic blood pressure measurement. So if you have anyone who has problems with hypertension or high blood pressure, you will probably see this as a daily routine for them to just check that everything is in order. So I'm gonna get to this later and gonna make my own version of this, but first let's try and understand how this works and what generally do we measure with blood pressure. You usually get two numbers. You get the upper and lower pressure, or systolic and diastolic pressures. The systolic pressure is the pressure at the heartbeat, so when the heart beats it's the peak, the highest pressure in your arteries, while the diastolic pressure is the pressure between your heartbeats in the arteries, so that's the lowest pressure, let's just say that. To measure it manually, you need this, which is a pump and an arm cuff with a manometer, and you also need a stethoscope. That's the main drawback of this method, is that you can't really measure your own blood pressure using this. You need another person and they need to be trained. But even in 2024, all of the literature suggests that this is still the golden method for non-invasive blood pressure measurements, even though there are thousands and thousands of versions of digital blood pressure monitors, and I think you'll get an idea of why is that during this video. But first of all, I'll show you how we can measure actual pressure with this, and we'll also experiment with a stethoscope, but we can make it electronic, as you will see later on. So the blood pressure measurement using this apparatus goes by putting the arm cuff around your arm, closing the valve that you can see here, and slowly pumping up the arm cuff around your arm. What that does is actually contracts around your arm and literally blocks the brachial artery, which is going through here, and you can listen using a stethoscope to the sound changes as you're decreasing the air. I'll try to draw that and demonstrate it a little bit better now. Let's take a look at how the blood pressure is measured using a stethoscope. So first of all, we want to put the arm cuff over the elbow about 1 to 3 centimeters, and in the red you can see the brachial artery, which we will be essentially blocking with the cuff, and we want to press a stethoscope on it. This method works by listening to Korotkov sounds that I'll explain now, and here in red you can see the pressure in the artery, how it would actually look like if you did an invasive measurement, and in pink you'll see our curve of the pressure inside the arm cuff. Now the yellow peaks here are the Korotkov sounds, and here's when they appear. When we started the measurement, we first pump up the arm cuff until some pressure that's above the systolic. At that point we slowly open the valve and start letting the air out slowly. Once that pressure reaches the systolic value, we can start hearing the pulsations. As it starts going down, the pulsations will first get louder, then the sound will get lower and lower, until one point it completely disappears, and that's the point where the Korotkov sounds disappears, and that's the point where the pressure inside the cuff is actually equal to the diastolic pressure, and that's how we actually measure the systolic and diastolic pressure using this method. I hope that the drawing explained how this works nicely. If you have any further questions, please let me down below and I'll be happy to clear any things out. But let's now concentrate on the digital ones. So while they are generally less accurate than the manual method, they are much more easy to use because it's just a press of a button and it starts inflating the cuff. You don't need anyone else to use it next to you, and the new modern ones can even can connect to your phone and do many other things. And they also, one thing that you can't do with this so easily is measure your heart rate. They just provide it straight out of the box. So let's do a deeper dive on how these work. Let's take a look at how automatic blood pressure monitors work. Of course, not all of them work the same, and it's a company secret what algorithms they use, but I will describe the Sapinski method or the Geddes. They work in the same way, just with different coefficients. So we can differentiate three different parts in measuring the pressure, and we control. There are three active components, two of which control, which are the air pump and the electromagnetic valve, and there is an adjustable valve which lets out the air the whole time during the measurement. So the first segment, we are actually pumping up the arm cuff, so the air pump is on and the valve is closed. In the second segment is where we actually do the measurement. The pump is off and the valve is still closed, but only the adjustable valve is letting air out. And in the third segment, we just let the air out with the valve. So the blood pressure monitor actually pumps up around 30 millimeters Hg above the systolic pressure, so it does a rough estimation when it's pumping up the arm cuff. Now let's take a closer look at the second segment. You can see it here. Now if we filter that signal, we can see this red line, which are the pulsations you can see in the pink line, just with detrended literally, and in the yellow you can see the signal envelope. Now we want to get all of our data from that envelope, signal envelope. If we find the max value of that envelope and find the time at which the max of the envelope occurred, we can actually estimate the mean arterial pressure. Now, the Geddes-Sapinski method works by having different coefficients of how high we want to go for the systolic and diastolic pressure. So, for example, in this method, for the systolic pressure, we want to have 40% of that amplitude of the envelope. This is that orange dot here. And if you look at the time at which that dot occurred, this is the systolic pressure, and for the diastolic pressure it's 80% of the envelope max, and if you look at that point it's the diastolic pressure. Of course there are more advanced algorithms, but these are some of the most commonly known algorithms used in digital blood pressure monitors. Now that we have an idea of how these work, let's see what we take to make our own version of this. First of all, this topic is kind of close to me because my grandma suffers from hypertension, as most people her age. So I was always curious on how these devices work, and that's why I made those devices the part of my master thesis project, and that's why I also made the project completely open source, both on Element 14 community and on GitHub. If so, anybody interested in that topic can just learn about them and see how reliable they are, and how you can actually use those measurements the proper way that the digital devices produce. So one big disclaimer here, what I will be making here is not a medical device. It's an experimental device, and it's just for experimenting with different algorithms and just generally learning on how we can measure blood pressure. That in mind, the first item in my safety requirement list, in my system requirement list, is safety. So by safety, we can't be connected to the wall at any shape or form, neither power or data. That's why I want to have complete USB isolation, optical isolation. There are chips for that. And I want complete power isolation. I will be using an isolated power supply. And besides that, the device doesn't even have to be powered from a computer. We can just use a battery. That's the first and main thing. The second thing is I want to measure blood pressure, of course, as you've seen. And I'll be taking literally parts from one of these old devices because they're rather cheap and they have everything you need. We'll need an air pump, an electromagnetic valve, and we'll need a constant valve that we can adjust how much air leaks out of the system, which is the part when the arm cuff is completely inflated and it slowly deflates. It's adjusted by that valve. Besides that, I also want to make my own stethoscope. So by making my own stethoscope, there are digital ones that you can connect to your speaker literally and listen to your heartbeat, but they're rather expensive. So through exploration and some literally playing around with this stethoscope, I managed to make it electronic so I can connect it to my device, and I'll show you how you can do that as well. Besides that, I also want a PPG clamp. Those are the clamps that you've seen put on your finger that can measure your oxygen saturation and also your pulse. They can also be rather useful for measuring blood pressure, especially the diastolic blood pressure, as I will show you later in the video. And last but not least, I wanted to add an ECG chip to the whole device, just to have something that I know has accurate heart rate measurement, that I can do accurate heart rate estimation and compare the results from other methods to this. Let's dive straight into electronics for this device. Let's go item by item from the requirements list and design our electronics around it. So first things first, that's the safety. So we have two parts for the safety. We have the USB signal isolator, which is done with this IC right here. And all of the components around it are just the recommended layout. And here we have a power isolator. So this is an error here. The part number is wrong. It should be 0511, but you'll find that noted in the on the GitHub page. So besides that, we also want the device to be battery powered. So let's go to the power section. There's another mistake here in the protection circuit. The transistor needs to be flipped. But besides that, we have the protection circuit, we have the charging circuit, and we also have, to be able to actually use the battery power, we need to step down that voltage from 3.7 to 3.3, or actually even step it up when the battery gets to 3.0 volts, for example, to 3.3. This is why I went with this buck boost converter, which is a great little package, a bit of a hassle to solder, but you can do it with a hot air gun. So this is a buck boost converter, and it will output 3.3 volts at any voltage of the battery. To turn actually on the whole device, we have a button connector which just temporarily turns on the buck converter, but the power latch is actually driven up by the Pico, so that in the case if we want to turn off the device, we can just drive that pin low and it will turn off the regulator. So the next important thing is the blood pressure measurement. So these are the schematics. This includes three main things. This is the air pump control, valve control, and pressure sensor measurements. So for the controls, it's just a simple MOSFET that we can control with PWM or just high and low. I've also added this optocoupler if you want to connect to an outside device and trigger it from our device. Also, this is a boost converter that I added because most of those things run in commercial blood pressure monitors run at 6 volts, so I added a boost converter for that. Besides that, this is the critical part of our system. This is the sensor I've used because it was widely available. One thing to note here, the pinout is wrong in the datasheet itself. Some pins need to be turned around, which you can also find on the GitHub page, but the thing to point out here is that instead of the normal HX 710 or 711 AD converter, I went with an instrumentation amplifier, which you can actually adjust with a potentiometer to get the range you want and also get readings much faster than the standard 11 Hz from those ADCs. And I've added some Schottky diodes for protection to protect our microcontroller. This of course means that we need to calibrate the whole system so that we can get accurate pressure measurements, because we can turn the potentiometer as much as we want, and I'll show you that in a little while. Let's just go through the rest of the electronics. The next thing we want to do is the stethoscope. So in the end I didn't really end up using any of these. These are the three circuits I wanted to design and try out for actually conditioning an aux input. But in the end I designed my own electronic stethoscope, and I'll show you that as well. Also, we said we want a PPG clamp. That's just an I2C connector. So I have both I2C0 and I2C1, and I've added connectors for both of them, as well as pull-up connectors with jumpers, so we can expand the system as much as we want. Next thing we have is the ECG. So I did a custom layout of the ECG chip that can do the morphology analysis with all of the proper filtering as recommended in the datasheet. And I went with the popular AD8232, and it just works pretty good. And in the end we said we want some wireless connectivity, so this is why I went with the Pico W. Great number of pins, also has wireless capabilities that we want, and the support for it is pretty big because the community around it is pretty big. Those are all of the schematics. Let's take a look at the PCB design. So this is a 4-layer PCB, top and bottom layers are signal layers, and we have two middle layers which are ground and 3.3 volts. So as you can see at the start, the top left corner is dedicated for the USB connector, and I've added these cutouts to make it completely isolated. So the planes are cut, and this red plane is actually the ground from the USB connector. So there is no kind of connection going from here to here, so that it's completely isolated. On the left side here we have the battery protection and charging circuit. I tried keeping the noisy stuff like the buck boost that you can see here and the boost converter that you can see here as far away as possible from the other stuff, and tried also keeping it away from other stuff, the ECG chip here, as well as the small instrumentation amplifier here, because they can be rather sensitive. And I've placed all of the components on one layer to make it easier to just solder everything. And the top part of the board here is for the aux circuits that you've just seen. If we go to the 3D view, this is how the whole circuit looks like. So the important thing is to have, of course, the USB connector poking out so we can actually connect to it and make an enclosure around it. And these are the isolation chips for the data, and this is the isolation power supply. And for the connectors, I went with the nylon 2.54 connectors. They're available everywhere and they're pretty easy to crimp. So that would be it about the whole pretty much electronic side of things. Let's do the calibration process now. As I mentioned in the electronics, the pressure sensor is connected to the instrumentation amplifier, and we can adjust its gain using the potentiometer. So the issue is, how do we actually know what kind of pressure we are measuring? We can do the calculations based on the potentiometer resistance and the datasheet of the instrumentation amplifier, but I wanted to make sure that I'm getting the accurate values, so I made this test rig here. Now, as you can see here, it consists of two syringes, which you can adjust using these hand screws in the back, and it has 3 pressure sensors with this manifold right here. So how this works is actually you connect the pressure sensor to this port right here, and you increase the pressure in the system and keep it at a constant level using these screws here. There are two sizes of syringes, one the bigger one so you can increase the pressure more rapidly, and the smaller one for doing smaller increments when increasing or decreasing the pressure, as you will see soon. And one more thing, I have 3 pressure sensors here just because I had them lying around, and in this way, if one of them is not correct, I can see it by the other two's being close. This is what actually happened here. This one in the middle, while I thought it was really good and used it from the beginning, turned out it wasn't showing good values compared to these two. So in the end, I just used the other two for the calibration process. So the calibration process goes, besides connecting this, going through the full range. First, actually setting the pressure to 40 kPa, or that's around 300 millimeters Hg, and setting the potentiometer so that the output voltage of the instrumentation amplifier is somewhere around 3.3 volts. And then from there I went in small increments at 1 kPa here and measured the ADC reading so I can map out everything, and I did a few passes for that. I'll show you now the computer screen with the table where I have all the recorded data. You can see the whole table here. And in the end, just using the least mean square method, I estimated this line here. So we are expecting a linear response to the pressure, and that's what we got. And using these parameters here, we can convert the ADC values into actual pressure measurements. So that sums up the calibration process. It's a bit tedious, but it turned out pretty good in the end. Now that we're done with the electronics and the calibration, it's time to go into the CAD model, design the case around this so we can finally get to programming and testing it. This is the board exported from my EDA software with all of the components, the necessary components populated. So the main thing besides this is, of course, first the pneumatics. This is how they look. And I put them around the PCB. So we have the electromagnetic valve here. We have the pump, all of the necessary tubing that goes to our sensor. We have the small adjustable valve, and we have our arm cuff connector. This is a custom one I designed. It's still a work in progress because it's leaking a bit of air with my current print settings, so that's something I still need to do. Besides that, we have the GX connectors, which you can see here in the back for connecting all of the other stuff. We have the charging Type-C connector. We have the battery and its holder. This is an 18650 cell. I've also added a small speaker to the side, as well as an audio jack, which are my plans to get it to work a bit better with the stethoscope that I will show you. And all of that fits in this box here. So I first placed all of the components around and designed this box around it. As you can see, it has indentations for letters. Because I have only a single color printer, I printed all of those letters with 0.2 millimeter smaller dimensions so that I can glue them into place here. And if we turn that on, you can see how that will look in the end. And of course, on the top we need the lid. So the lid has a small I2C OLED display that you can program to do whatever you want. 2 buttons for controlling the device, and these here are the RGB LEDs, which you can also control. They're NeoPixel addressable LEDs, so you can control them to your desire. I just put some of the text that I want to show here, and of course we have the letters there as well. Before we get to the software and testing, I mentioned 2 other things that I will be making for this project. One of them is the PPG clamp that goes on your finger to measure your saturation, but we will be using it for something else, as you will see later on. So it's just a microelectronica oximeter 5-click, and this is a 3D printed clamp around it. And for the cable, it just connects to the I2C bus on the board, and that's pretty much it. I used some fancy stuff to tune how hard the clamp works, or I just took a spring out of this, and it worked great. I just put some padding here just to make it a bit more comfortable and easier to align the finger on the sensor itself. The other thing I mentioned was the stethoscope. So I took an old stethoscope, a pretty old one, that's why it's not working now nicely at the moment, because there's a crack here, and turned it into an electronic one with this thing here. So if you look at here, there's a small piezo microphone here, and it's just connected to an amp circuit, which then just sends an analog signal to the ADC of the Pico, and we just read that signal, and that's literally all of our stethoscope reading. Now, before we get to the main part of this video, which is the testing and the data analysis, let's do the software now. The first code I'll be showing you is the Raspberry Pi Pico code, and I've written it using Arduino IDE. I didn't want to use MicroPython, I wanted to get the best performance out of this board. So I've split it into a couple of files just to make the whole code more readable and easier to edit. The first file is all of the libraries, all of the pins, parameters, variables, and I made sure to have brief descriptions of each variable or each parameter so that anybody can easily tune the code to their likings. Of course, we have the main function, which includes the setup function, where I do the usual of setting up the pins, serial, Wi-Fi, and the timers. So the next thing I will go to is the timers. So Pico has this great library with 4 timers, which essentially lets you make 4 threads so you can run 4 tasks at the same time. And these functions are called every set amount of microseconds, which you can see here, for example. Sorry, not here, but here with the period parameter. And here I have those timer functions which handle different things, like the LED handler, the communication handler, or the just acquisition handler, or the sensor handler. One more thing to note here is how the commands are done. They're done in the same in a similar way to G-code commands. So there is a command, for example, C3 command 3, and it takes one parameter which is 1 or 0, and there's just one blank space between those, and that's how you actually communicate with this device, by sending it those commands. If you look on the Element 14 community or on the GitHub page, you'll see a Google Doc actually linked with all of the commands available, as well as their examples and how to use them with this device. But I've also done a graphical user interface to make it even easier to use this, so let's go and check that code now. Here is the graphical interface code. So I have written this, of course, extremely fast, as every student does, so this is all literally in one file and fixed to the 1440p resolution of my monitor, so this needs a lot of work to actually get it to a really nice working place, but it works, it got the job done. I've just separated the code into regions so that it's more compressible, so that I don't have to scroll 2000 lines of code. We have the libraries, and the most important thing here to note is that I'm using PyQt5 for the actual graphical interface, and I'm using threading to have a few threads for things like communication and just keeping the whole application alive. And that's pretty much it. All of the other things, for example, this is how I decoded the data. You can see this also in the Raspberry Pi Pico code by how the message is formed, and I'm just doing the process in reverse to get the data out of it. So some of the main things of this code is that I'm showing everything in real time. You can also check which COM ports are available, which is done with this here, and it's a drop-down menu, so you can actually select your board, and you can record all of the data into a CSV file for further analysis. Let's switch over now to see how the graphical interface actually looks like. This is how the graphical interface looks like when we launch it. So as I mentioned before, you can here select the COM port that's available. I don't have anything connected to my PC now, and you can also here adjust the baud rate so you can match it to your microcontroller. Besides that, most of the screen is taken up by these four things here, which are live graphs, and they update in real time with the data coming from them, as you will see later along in this video. You can turn on some of the channels or off depending on what you actually want to record with any of your tests. You can turn on or off the data stream, and you can also record the data down here. So you can just enter your file name, enable the recording, and it will record everything that you pretty much see on these graphs into a CSV file. You have the blood pressure monitor controls down here, so you can control the stream, the pump, and the valve. And this bottom left corner here is a work in progress where I want to add automatic blood pressure measurements and stuff like that. Okay, so let's see the final project now. And the project is finally finished. I love how everything turned out. I love the case. I especially love all of the colored lettering inside. This would have been much easier having an AMS or something like that. But even just gluing them into place, it was a bit tedious, but I just love how it turned out. And just color matching all of the connectors so they're the same color, and it's kinda harder to mismatch what goes where. It's a pretty nice touch. Also, the ECG splitter, which I haven't shown you until now, I just made it so you can easily connect banana jacks for your ECG electrodes, just so you can move a bit more freely when you're connected to this device. Let's go and test some basic features of it, like the PPG and the stethoscope, and then I'll describe the testing procedure that we will conduct, and finally we can get to the main part of recording some actual data and doing analysis on it. Finally, time to do some testing. So here's the finished device with two of the modules connected. So I have connected the stethoscope and the PPG clamp, and I've connected the device to the computer. So let's first power it on. You can hear the sound that it connected to the computer, and you can also see the blinking LED. If you listen closely, you can hear the speaker reacting to the stethoscope. I'll bring that over here, and I'll keep the PPG clamp here in frame. So now let's switch to the graphical interface. Now you can see that when we check here the COM ports, the computer has found COM3, which is our device, and we want to set the baud rate to this, and we can then connect to the device. Okay, so we're connected now. So for this test we want to turn on the PPG clamp. As you can see by the small red light down there, it's turned on now. We want to enable the stream, and we also want to do that for the stethoscope. So now when we click enable here, you can see that the signals are coming through. And for example, if we open up and close the PPG clamp, you can see the signal changing. Let's see what happens when we put my finger inside and keep it there for a bit. You can see some oscillations, but you'll get to see them now properly. And here you can see the oscillations, and if I keep my finger really still, those are actually my heartbeats. Also, if I take the stethoscope and touch it a bit, you can see that changing the signal as well. I'll now put the stethoscope and be quiet to my neck, so you can see the heartbeat signal there as well. As you can see, it's a pretty clear signal, and you can see that they both match up, both at the top and at the bottom. So the graphical interface and the device, they are both working pretty good right now. So let's connect the ECG and go for a full testing method, and then later I'll show you how I analyzed all of the data. So now that we know that the basic functionalities of the device are working, it's time to develop a testing procedure so we can compare it to a commercial device. This is the commercial device I will be using. This is a Value BP2. It's an FDA cleared blood pressure monitor, and besides the systolic and diastolic pressure, it also provides you the reading or the estimation for the mean artery pressure, which is the top of the peak, if you remember from the drawing before. So now how the procedure goes is that the person that the measurements are conducted on needs to first sit on a chair for, let's say, 10 minutes. It's recommended in the literature 5 to 10 minutes, sitting silently. Then we measure the blood pressure using this device, and we can do that a couple of times if you want, 2 or 3, to get the mean value of those readings. And there needs to be at least a minute between the measurements. So that's the first thing we do. After that, we actually conduct measurements with our developed device. First of all, we need to place the electrodes for the ECG, and for that I will be using these sticky electrodes that you can see here. So the placement that we will go for is left arm, and right leg, as you can see on the drawing here. Now, the other thing that we need to do is place all of the other stuff on the arm. So that includes stuff like the arm cuff, which should go about a centimeter to 3 centimeters above your joint here. Then underneath that goes the stethoscope, right somewhere around here. And on the same arm, on your index finger, you want to put the PPG clamp, and you shouldn't press too hard on it. After that is done, you can run the test, as I will show you now, and when you collected all of the data, we can get to the data analysis. So let's do a full-fledged test now. Now that we know the test procedure, let's do a full test. I've already measured the blood pressure of my friend using the commercial device, so now I'm in a hurry to measure using our device as well, so that the measurements are as close as possible together. I've enabled all of the streams and connected all of the electrodes and the device as I've shown previously. So let's kick off the recording, and now we can go ahead, turn on the pump valve and test everything out. We want to inflate to around 200 just to make sure, and slowly deflate it. Here we can take a look at the value. You can see the cuff slowly starting to deflate here, and make sure to keep the orange signal in mind, so there's no oscillations on it now. But as the pressure in the arm cuff is slowly decreasing, you'll start to see right now the small pulsation starting. That's the blood flow being re-established in the finger. And you can also see a similar thing in the stethoscope signal, but that's something we'll analyze in the data section of this video. And now we can completely deflate. Now that we've recorded all of the data, it's time to do some data analysis, and I will be doing that using Python and Google Colaboratory, which I suggest you try using as well because it's extremely easy to use and you can use it even from a tablet if you want. Here on the left I have the file that we've just recorded. Here I installed just this library that we will need, you'll see why, and this is the rest of the libraries I will be using. So let's go to the code. Here I'm just loading up the data and storing them in their own arrays. Nothing special or smart here. The only thing I'm doing here is setting the time. So because I'm sending the time as millis command from the MCU, I'm just setting the start time to 0 by this and dividing everything by 1000 to just convert it to seconds because we don't really need to play around with milliseconds. So first of all is the pressure signal. This is some additional filtering I have just to make the signal look a bit better, and here I will plot out the whole signal. Oh yeah, sorry, didn't run this code above. Now we can run this. And now if you see, this is how the pressure signal looked during the blood pressure measurement. Here you can see that we turn on the motor, the pump, and we pump it up over 200 millimeters Hg, and then we slowly decrease the pressure and let the rest of the air out at the end. So we're interested in this central section here, the deflation segment, and you can see that part here. You can already start to see some oscillations here, and we actually want to analyze those and get the blood pressure reading from these oscillations here. To do that, we need to detrend the data. This is why I'll be using the OBS.py library. You can find the code here. You'll be able to find the code both on Element 14 and on GitHub if you want to play around with the parameters yourself. This is how that detrending looks, and we end up with a signal like this that I've plotted here as well. If you look at this, it can remind you a bit of the signal that I've drawn for you for how the automatic blood pressure monitors work. Of course, it's not perfect because these are actual measurements, so there will be noise and stuff like that. But this is a filtered signal and it should do the trick for us. Next thing we want to do is to actually try detect the peaks. We can do that here. So these peaks actually correspond to the heartbeat, and we can check that this actually gives us the correct measurement estimation for the heart rate. Now we need to estimate the envelope of this signal, which will this part of the code do. If you have any further questions, I won't go into too much detail into the code here, but if you have any questions on how any part of this code works, please let down below in the comments and I'll let you know. So this is the estimated envelope. Now we want to find, as you remember, the maximum point and then find the 80% and 50% lines. We will do that here. If we do that here, now you can see this here is the maximum point, this is the 80%, and this is the 50% line, and this is the 0 line. Now if we use the time, so you can see the time scale down here for when we detect the mean arterial pressure, the diastolic and the systolic pressure, we can go back to the deflation curve, which is here, and to actually figure out what kind of pressure that is in the air cuff at that point. And that's how we actually estimate the blood pressure. So this would be 120 something with 80 something, with the mean arterial pressure being a little underneath 100. We'll compare that to actual, here are the actual measurements, to actual results from the commercial device at the end. Okay, so that would be how most blood pressure monitors work. The simplest algorithms that are in the literature. There are of course other ones, but every company keeps them a secret. Let's now look at the stethoscope signal. Here you can see some higher beats if you touch the stethoscope, but we're interested in this middle section here. So we will use the same deflation period as we did for the pressure signal, and we can see something like this. I mean, you can still see the oscillations and the heartbeat. If we do some peak detection, you can see that, I mean, this is highly dependent on how you filter the signal and everything like that, how you use the stethoscope. But you can see that from this peak here, the oscillations become pretty regular until the end here. So if we assume that this peak here is when we actually start hearing those Korotkov sounds that I've described to you in the manual blood pressure measurement, we can actually try and use this time period, this time point here as a rough estimation for the systolic pressure. If you look at the delta between peaks, you can see that they become rather regular here, and we can do a rough estimation of the systolic pressure, and it turns out it's around 124, and the heart rate is around 71 using the peaks here. And if we compare that to the pressure above, we can see a heart rate of 72 and a systolic pressure of 127. So it's a pretty good estimation this time. Next, let's go to the PPG clamp. So let's look at this signal. You can clearly see where the blood flow wasn't as in the other part. So this middle section here, this is where we were actually having pressure on the artery with the air cuff. So if we look at the deflation part, let me run that code here, you can see this. So as the deflation is going on and the pressure is dropping, you can see that the oscillations start at one point. Now, usually this can be used to determine with higher accuracy when the flow of blood is laminar in your arm, and that's the point where you want to actually detect the diastolic pressure. I tried doing that here, but the results just weren't good enough, as you will see. So we are again detrending the data so we can analyze the peaks a bit easier, as you can see. And clearly this peak here, if we do the peak detection, would be the one that starts with all of the oscillations. But if we try estimating the diastolic pressure with it, we're gonna get something around 94, which is rather higher than our other estimations. But that's still, I mean, it's a highly experimental method for me like this, and also data filtering, stuff like that. The last part we want to analyze is the ECG. So the ECG measurement for me this time was rather noisy for some reason. Maybe I put one of the electrodes not so good or something like that, not so sure. But this is the full signal. If we look at this segment, we can see that we can clearly find the R peaks of the ECG complex, and using them we can also calculate the heart rate and compare that to the other methods. We can also use this data to calculate heart rate variability, stuff like that. You can read more about it, won't go into too much detail here. And here we can also use this signal to actually extract a single heartbeat here and how a QRS complex looks like. Now, here are all of the final results that we have. And I'm just gonna put on the screen the screenshot from the commercial. So using our pressure sensor, we measured the blood pressure of 127/83 with the mean arterial pressure being 97, while the commercial one did 121/75 with the mean arterial pressure also being 97. So the map is pretty much spot on, which is a great thing. As for the measurement, they're not too far apart. Just for your information, a device is considered to be A class if it's within plus or minus 15, so I'm rather happy with these results. As for the pulse rate, the device said 75 per minute, but there were a couple of minutes between the two measurements, and you can see down here that all of the methods yielded a rather similar heart rate measurement. As for the experimental methods, you can see that the systolic pressure estimation was rather good using the stethoscope, but the diastolic pressure was not as good using the PPG clamp. But on some other tests I conducted, it was literally the other way around. So there is a lot of things you can actually fine-tune and adjust. Thanks so much for watching this video. I really hope you enjoyed it, and I really hope that I managed to demystify a bit the whole area around blood pressure monitors. If you have any questions or comments, please leave them down below. All of the code, CAD files, Gerber files for the PCB, everything is available down below on Element 14 community. And you can also follow the GitHub repo for any new updates that I will be doing for this project later on. Really hope you enjoyed it once again. See ya in the next video.